Arden Labs, specializing in high-performance software consulting, training, staffing, and development. Module 14, Profiling and Tracing. You are now watching Lesson 14.2, Stack Traces.
I'd like to take a little time up front to teach you how to read a stack trace in Go. Stack traces are very powerful, and there's some basic things you probably know already, and there's others that a lot of Go developers don't. So let's get into it. So on line 7 here, I've got the main function, which calls another function called example. Now, as we move into example on line 12, we see that it's panicking on line 13. I'm forcing a panic. Now, if I were to build and run this program here, if I build it and run it, we see the stack trace, and you probably have seen stack traces like this before, where we're going to see here that at the bottom of the stack trace is where we started at the main function inside the main package, and we were on line 8, and then we got to the example function in the main package, and then we were on line 13 when the panic occurred. So 8 and 13, right? If I come back here, there's line 8, there's line 13. We know where the panic occurred. So most people can figure that out pretty quickly. But what a lot of people don't realize is that these values here have a lot of meaning and can give you a lot of information, more information about what the state of your application was in. But to understand these numbers, we've got to kind of go back and look at the code and begin to understand our parameters and what we're passing in. So let's take a look at the call to example. If you see the call to example, we have to pass a slice, a string, and an integer. Well, let's map out on the board exactly what we're passing in this code. So on line 8, when we make the call to example, we're passing in a slice. Now we know a slice is a 3-word value. We know that slice has a pointer. In this case, it has a length of 2 and a capacity of 4. We see that on the construction call with make. We're also passing in a string. String is a 2-word value. There's a pointer and a length, and we know the string hello will have a length of 5. And then we have another word, which is going to be 10. So if we look on the board, I've got 3 words of data here. And if I go back to the stack trace, I want you to notice that there are 3 values separated by commas. And with these first 6, did I say 3? Sorry. There are 6 values separated by commas. And these first values represent the words of data that we're passing in. So if you see that, we'll take a look at the first 3. We got the address, the number 2, and the number 4. Address, number 2, and number 4. Address, 2, 4. That's the slice value right there. Length and the capacity. If we look at the next 2 numbers, now what do you see? Address, length of 5. Now what you're looking at is the string value. And finally, A in hex is 10. So if there were return values for this function, you'd see more comma delimited numbers. But the first ones are always going to represent those words of data for the input. All right, pretty cool, huh? Let's take a look at another example here. Go into example 2. So this time, what we're dealing with is a function example that takes really a half a word of data, right? 4 bytes, 3 bools, and a uint 8. And we pass true, false, true 25 into it. So what happens when this program panics? Well, let's move over to example 2. Let's build it. And let's run it. So this time it panics again. We're on those lines of code we see. But because those 4 values that we're passing in are each a byte, a half a word of data, we get one big number here listed in the stack trace. But no big deal. We just have to know what our system here, and we know this is a little endian system, and you have to know that every byte represents 2 digits in this number. So since these are single bytes, 2-digit values, we can read these bytes from right to left. And we get 0, 1 for true, 0, 0 for false, 0, 1 for true, and 19 hex is 25. And the rest right now is just garbage because it's only a half a word. So it's really, really amazing here that the stack trace is not just telling us lines of code, it's also telling us the data at a word level of what's coming in. If we know the size of our bytes, like that single byte that boole's 2 digits. If you had an int16, it'd be 4. We could read that value and know everything that's being passed in. It's so important that when we're writing code, we're writing APIs that are as precise as possible. Not only does it help with readability, it helps also with debugging. Now I'm going to go back to the first example because there's another thing I want to show you here. So let's go back to the first example and we'll run it again. And another value in this stack trace that a lot of people don't know how to work with is this one right here. You see the plus 072, you see here plus 039. So what does this value represent? This value represents the PC or instruction pointer offset of where the code was in that function at the time of the panic. Now we have to remember on the systems that we work with, usually the PC or IP instruction pointer represents the next instruction that would have gotten executed. It usually increments ahead of the instruction that's being executed. So how can we use this 39, this hex 39 number? Well, we have a binary. So what's nice is that we can go into another tool called Object Dump. It's a tool that's part of the Go tool chain. Now, there's 2 parameters that we basically need here. We need the capital S to tell Object Dump to give us an assembly language representation of this. And I want to filter this out for main.example. So the lowercase s is kind of like a regular expression of just pulling out that one function out of the whole listing. And then we just have to give it the name of the binary there, example 1. And what we're going to see is an assembly representation of the example function, because that's all I asked for, main.example. Now remember, the value that we saw in the stack trace was hex 39. So watch what we're going to do. We're going to take the starting address for example, and we're going to add it into our calculator. Let's move this into a programming calculator here, where we're going to be in hexadecimal numbers. We can paste that in there and add hex 39 to that value. We end up with 104E1F9. Well, guess what? There it is, 104E1F9. We're exactly there. That's what that plus 0x39 is. That's the next instruction that would execute if things hadn't gone in this terms of a panic. And you can see the call right above it is to go panic. And this UD2 instruction really is an undefined instruction. It's designed right now to cause the program to fault if it's ever executed, because we should never really get there. But you can see now how that plus 39 or plus 72, we can do that. You can see how you could leverage that. Now, if you ever need this, I feel sorry for you. I've never needed it. But I just want you to share with you that that value is listed and how you can get to it. So these are stack traces in Go. I don't want you to walk away from these stack traces. Leverage them to help you figure out what is going on when that panic occurs.